Hi, Assalamualaikum, and good evening, everyone. We have covered in my lectures 1 and 2 two topics. One is how to determine the Lewis shapes or Lewis structure of a molecule or an ion, and the second lecture was to use valence shell electron pair repulsion to determine the shape of the molecule for that particular arrangement of atoms. Now, next we are going to go into hybridization. But before we go into hybridization, it is quite important that students understand what are the shapes of atomic orbitals. Now, everybody recalls that in an atom there are at least 3 or 4 types of atomic orbitals. You have the s orbitals, p orbitals, d orbitals, f orbitals. Yeah. So what actually determines and what are the shapes of atomic orbital? Now, an atomic orbital actually does not have a well-defined shape because the wave function characterizing the orbital extends from the nucleus to infinity. The plots of electron density in an atom falls off rapidly as the distance from the nucleus increases. So as you move away from the nucleus of an atom, away from that nucleus, the electron density or how much electron is present becomes less and less as you go away further from the nucleus. By drawing a boundary surface diagram that encloses about 90% of electron density in an orbital, we can roughly give an estimate of the shape and the relative sizes of an atom. Because we all know that electrons do not stay put. Electrons move around, and when moving around and moving very high speed, because electrons are very small, they move at a very high speed. So the presence of electrons from the center of an atom is very much high. The presence or the electron density is very high, very close to the center. And as the distance becomes larger from the center to the outside, the presence of electrons becomes less and less, so the electron density. So when we draw the shape of the movement of the electrons, that defines or that gives the shape of the orbital. So the size, s orbitals have a particular shape that belongs to them. S orbitals are generally, they're all spherical in nature. P orbitals are dumbbell shaped. D orbitals are shaped generally like butterflies, and those shapes are determined by the way or the map of electrons moving in that orbital. And the size of each orbital increases with increasing value of n, where n is the shell, the electron shell. So however, the shapes will always remain the same. So for example, 1s orbital is spherical, it's like a ball, but when you go from 1s to 2s, 2s is bigger, 1s is smaller. And when you go from 2s to 3s, 3s is bigger and 2s is smaller. The shapes are still the same. They are all still spherical. Now, the region in which electrons moved, it's called the orbitals. This is where the orbitals are. Where the electrons move, that's called the orbitals. In terms of wave, orbital describes the region in space where electron density is very thick. In terms of particle, the orbital describes the region in space where there is a high probability of finding an electron, because that is where the electrons move a lot of the time, 90% of the time. So the chances of you finding the electrons in that area is really, really quite high. So for the purpose of CHM477, there are three main types of orbitals that we will cover. The s orbitals, which is spherical in nature. Oh, by the way, this is on page 11, excuse me, on page 11 of the notes that I gave you, yeah? So you can look at the printout of the notes and make some notes as we go along. Orbitals are spherical in nature, as I said before. P orbitals are dumbbell shaped in nature, and D orbitals are butterfly shaped. Now, moving outwards from the nucleus of an atom to the outer shell, as I was telling you earlier, the shapes of these orbitals do not change. However, the size of the orbitals increase as the shells increase. When I say the shells increase, that means the shells become from shell 1 into shell 2 into shell 3 and so on and so forth. So if you look at this diagram here, can you see it? This is a spherical shape, so we know it is an s orbital. 1s is spherical, it is small. Now 2s is also spherical, but it is bigger than the 1s. And 3s is also spherical, but it is bigger than the 2s. So this is a qualitative representation of what is the size of a 1s orbital, 2s orbital, and 3s orbital. So if you look at this diagram here, this actually is where the electrons can be found as they move around in that orbital, and drawing 90% probability, you will get this sphere. So is that clear? What is the shape of the s orbital? What's the shape? Yeah, I hope you answer spherical. Okay, next I would like to, I'm sure you have learned this before in previous classes, but I would like, if that is so, then I would like to make some revision. Now, the second type of orbitals that we are going to deal with in 477 is the p orbitals. Now, p orbitals have the shape of a dumbbell. Yeah, look at this shape. It looks like a dumbbell. Who among you go to the gym a lot, or you exercise a lot using weights, you may recognize that this shape looks a lot like a dumbbell. Yeah, and for p orbitals, there are three orientations at which they can be found. They can be found along the x-axis, so that orbital is called the px. They can be found around the y-axis, and that orbital is called the py orbital. Oh, excuse me. Cancel. Okay, and they can be found around the z-axis, where that orbital is called the pz orbital. So according to where the orbitals or the dumbbells are plotted, you call them accordingly. So if you combine the three, the px, the py, and the pz, the p orbitals look a lot like this. Yeah, can you see this? Yeah, so that's your pz, that is your py, and that is your px over there. So if you break them up like this, this is a more round shape presentation. This is a little bit elongated. You have the px, the py, and the pz orbitals. And again, well, there is no one p orbital. In the shell number 1, you don't have p orbitals. You start getting p orbitals in shell number 2. So you have 2px here, 2py, and 2pz. There is no 1px, 1py, or 1pz. In orbital, in shell number 1, there is only s orbital. Yeah. And moving along, I hope you understand the p orbital and the s orbital for now. Moving along, I would like to introduce you to another set of orbitals, which are called the d orbitals. Electrons who move in the d orbitals move around in the area that looks like butterfly. Now, butterfly shape, and there are 5 orbitals. If d just now you have 3 orbitals, you have the if p just now you have 3 orbitals, you have the px, py, pz, but d orbitals have 5 orbitals, and they are dxy, dyz, dxz, dx squared minus y squared, and dz squared. Now, these 3, the dxy, dyz, and dxz, look like this. This is your, that is your dxy, where the butterflies are located. The lobes of this butterfly are located in between the x and the y axis. So that is the x-axis, that is the y-axis. Can you see my cursor moving? That is your y-axis. So you have the lobes, these lobes, 1, 2, 3, and 4 lobes of the d orbital are located in between the 2 axes, the x and the y. That's why they are called the dxy. And in this case, it is 3 dxy orbital. Now, in the same argument, you have your dyz, where the lobes are located in between the y-axis and the z-axis. So that is your y-axis. That's vertically is your z-axis. So dyz has orbitals between these 2 axes. And along the same argument again, or along the same story again, your dxz have orbitals or lobes or probability where electrons will be found in between the axes of x and z. So you have dxy, dyz, dxz. So these are 3 of the 5d orbitals having the lobes, lobes, yeah, lobes of the orbital in between 2 axes. So they are 3 siblings. If you have a look at these 2, on the other hand, look at dx squared minus y squared right here. Can you see this? Now, dx squared minus y squared have the lobes of the orbital directly on top of the axis of x and y. On top of x, there are 2 lobes. On top of y, there are 2 lobes. And in this shape or in this orientation, the orbital is called dx squared minus y squared. And finally, number 5, orbital z, the 5th z orbital is, the 5th d orbitals is the dz squared, where there are 2 lobes along z on the z axis, and there is a little hula hoop. Can you see the little hula hoop? That's very pretty. A little hula hoop that is around this. Why your electrons move, your dz squared electrons move in this way? It is mathematically derived, yeah? From the mathematical equation, they solve for the probability of finding electrons, and it looks like the dz squared electrons move in this way, where there are 2 lobes on the z-axis and then a ring around this the center of the axis. And if you're wondering the mathematical equations, how they derive the mathematical equations, you can have a look at the top part of my notes where I have colored my writing in blue. This is the background of it. If you want, please read it. They use so much equations and series and so on and so forth in determining the shape of the orbitals. So I have covered your s orbitals, spherical in shape, 3p orbitals, dumbbell in shape, and 5d orbitals, shaped like butterflies and hula hoop here. Yeah. Now the orbitals dxz, dxy, dyz, and dxz have lobes between the axes, meaning that the movement of electrons in these orbitals are concentrated away from the axis, x, y, and z, whereas the dx squared minus y squared and dz squared have lobes on the axis, meaning that the movements of electrons in these two orbitals are concentrated on the x, y, and z axis. Yeah, the difference in nature of movement of these electrons in these 5 orbitals are quite important for you to remember, because they will actually play a big role when we are determining crystal field theory. So by now, I hope that all of you are going to be able to draw the s orbitals, the 3p orbitals with the axis and so on and so forth, and the 5d orbitals with the correct orientation of your 2 types. You have this type and the other type, right? Moving on to the energies of this atomic orbital, obviously when you have orbitals stacked in an atom, some of them will have very low energy. Very low energy means very stable. Some of them will have quite high energy. High energy means that they are quite unstable. Now, energies of atomic orbital, the energy of an orbital is determined by the value of n. N is the shell number. So shell number 1 has n equals 1. Shell number 2 accordingly has n equals 2. Shell number 3 has n equals 3. Okay? So right. If you look at this diagram, you're going to be able to see that in n equals 1, or in shell number 1, there is only one type of orbital, which is the 1s. And 1s has very, very low energy. Low energy means it is quite deep into the, quite close to the nucleus. Now, if you move into the 2s orbitals, generally into the second shell, this is your second shell, you find 2s and 2p, 1 orbital of 2s and 3 orbitals of 2p. And then going on to shell number 3, on layer number 3, you have 1 orbital of 3s, 3 orbitals of 3p, and 5 orbitals of 3d. And going straight to n equals 4, or shell number 4, you have s, p, d, and f. F, there are 7 orbitals, but we're not going to cover f orbitals for the purpose of 477. Now, in general, as the number of shells increase, the energy of the orbitals also go up. Yeah, but this is only true if you only have 1 electron, and the case of one electron is only occurring for hydrogen. A hydrogen atom single electron can occupy any of its atomic orbital. However, in the lowest energy state, or called the ground state, the electron resides in the 1s orbital. If there are no excitation, there is no energy being provided, external energy being provided, then you most times will find the electrons of the hydrogen to roam or to move in the 1s orbital. If energy is put in the atom, the electron can be transferred to higher energy level. It is said to be in the excited state. So if you provide energy into a hydrogen atom that has obviously only one electron, then that one electron can experience excitation. It can become excited. So you have excited state, and it cannot stay too long in the excited state. It will go down. It will go back down into the ground state, which is your 1s. That is only true, this arrangement of energy levels for the S, P, D, F, only true for one electron atom. However, when you have like so many other atoms, you have many electrons in one atom. So in a many electron atom, the energy of the orbitals does not only depend on its principal quantum number. Principal quantum number is n. Yeah. It also depends on its angular momentum quantum number. The total energy of a many electron atom also has to take into account the energy of repulsion between electrons in its orbital. So when you have more than one electron to deal with, you put one electron in one orbital, there is going to be interaction between that electron with another electron in the same atom. There's going to be repulsion because two electrons both are having negative charges. Then having negative charge, they will repel one another. Yeah. The factors of repulsion result in degeneracy of the different types of orbital in the same principal quantum number as shown below. So you're going to see that generally 1s is always at the bottom because it is very, very stable. In shell number 2, where you have 2s and 2p, when you have more than one electrons, you're going to find that the 2s is lower in energy compared to the 2p. And similarly for the 3s and the 3p, the 3s will have lower energy than the 3p. And the 3p will have lower energy than the 3d. So you can see here 3s, 3p, and 3d. And we actually expect to see that the 4s will have a higher energy than the 3d. But that is not true. The 4s in actual fact has lower energy than the 3d. 3d has a higher energy than the 4s, and I will explain this later. This is called the Outbound Principle. I'm sure you have also heard of the Outbound Principle. And within the same shell, the 4s, the fourth shell, or n equals 4, 4s is lower than 4p, 4p is lower than 4d, and going to the 5s is lower than the 4d. So this is how many electron atom arrange the energy levels of the orbitals in the atom. It follows that the order in which these orbitals are being filled up by electrons is from the lowest energy to the highest energy, as shown in the Aufbau principle. Or Aufbau means building up in the German language, building up. So the Aufbau diagram, I'm sure some of you have seen this. to draw the this is the order at which orbitals are going to be filled in by electrons. So we have 1s, and then 2s, and then going back 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on and so forth. So the Aufbau principle is saying as protons are added by one by one to the nucleus to build up the element, electrons are similarly added to these hydrogen-like orbitals. You add protons in the nucleus, you also have to add electrons in the orbitals. Otherwise, the charges will not be balanced. Now, as electrons fill up the orbitals according to the Aufbau principle from the lowest energy level to the highest, we can see that the elements can be arranged in groups according to the type of subshell in which the outermost electrons are placed as shown below. So this must be quite familiar to you, the shape of the periodic table. So the outermost electrons, if the outermost electrons are found in the 1s or the 2s or the 3s, 4s, the elements are placed on the left side of the periodic table. If the outermost electrons are located in the p orbitals, they are located on the right side of the periodic table. And if the outermost electrons are placed in the d orbitals, they are then, the elements are put in this bridge, kind of the blue part of this periodic table. So you call this the S block. This is the P block. That is called the D block. And down here is the F block. Actually, F block goes in between the D and the P. But never mind. Otherwise, it will become too long. Otherwise, our periodic table will be too long. So the F is located. This is called the Lanthanide series and the Actinide series. So that is how electrons are being filled in the orbitals that you are familiar with by now, the shape of each orbital. You have the spherical, you have the dumbbell, you have the butterfly shapes of the orbitals, and how the Aufbau principle is being used to fill in electrons one by one into these orbitals, and in the end, how the elements in the periodic table are arranged so that you have the S block, the P block, D block, and the F block. Okay? Valence bond theory states that bonds are formed by sharing of electrons by overlapping of atomic orbitals. Now, when you have two atoms approaching one another, yeah, imagine this, let me go a bit far. Imagine these are two atoms, yeah? These are two atoms far away from one another. When they are far away from one another, there's not going to be any interaction, because interaction can only occur when the atoms are close to one another. When they're close to one another, the orbitals, if you imagine this is your one atom and there are many orbitals around here, imagine, and the orbital of this atom and the orbital of that atom, when the two atoms become close together, they will start to overlap. When the orbitals overlap, the electrons can move and be shared between this atom on that atom. So overlap of orbitals allow for electrons to move from one atom to another. As long as there is no overlap between the atoms of two elements, there will not be any interaction, because electrons will not move from one atom to another. But when they approach one another, having an overlap of the orbitals, the overlap will allow for movement of electrons from atom A to atom B, and you get chemical bonding. Yeah, you get chemical bonding. So, just let me see. Can you see? Excuse me. Get chemical bonding. Yeah, you get chemical bonding. Now, valence bond theory states that bonds are formed by sharing of electrons and overlapping of atomic orbital. Now, when atomic orbitals overlap, the shape of the molecule is going to be determined by the shape and the orientation of the overlapping orbitals. So we are thinking, okay, if p orbitals like this is, for example, this is your pz, this is your py, so they are 90 degrees to one another. So if the overlapping pz and the py results in formation of molecule, then we expect the molecule to be having the shape of like this, the 90 degrees to one another. That is natural for us to expect that. However, there is a problem encountered when we apply the valence bond theory to ammonia molecule. Now, what do people see when they analyze the shape of ammonia molecule? They find that ammonia has the shape of a trigonal pyramid. The pyramid which has a trigonal shape, base. So how do they rationalize that shape? Because according to valence bond theory, this is not right. That shape that is seen in real ammonia molecule cannot be explained by the valence bond theory. Let's have a look at how valence bond theory determine the shape of ammonia. If ammonia is NH3, yeah, if the three NH bonds are formed from the overlap of three 2p orbitals on nitrogen with the 1s orbital of each hydrogen atom, what would the molecular geometry of ammonia be? Okay, now you have one nitrogen and you have three hydrogen atoms to make ammonia, NH3. So naturally, you are saying ammonia, nitrogen is 1s2, 2s2, 2p3. Here it is. This is the 1s, this is the 2s, this is the 3p. So 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 3 electrons in the 2p orbitals. So because the electrons are singly occupying the px, this is the py and the pz, we are saying, oh, easy then, because the hydrogen, 3 hydrogens, will simply put 1 electron on px from one hydrogen, another electron on py from the second hydrogen, and another electron to put in the pz from the third hydrogen. And we all know that these px, py, and pz are 90 degrees to one another. So according to this description, you are, while I'm recording this lecture, you are busy giving me messages in the Telegram group. Let's have a look. Okay, there you go. So many. Buka link dekat YouFuture. Okay, that's it. Thank you, Chef Putri. Okay, you have the, you are saying that if this is true, then the shape of ammonia would be like one bond like that, and H, one bond like this, and H, and another bond 90 degrees outside to that. So you would have nitrogen and NH, NH ke depan, and NH on the side. You're going to have 90 degrees bond angle between the three NH bonds. Yeah. If we use the three 2p orbitals, the bond angles can be predicted to be 90 degrees. However, this is not correct. This is actually wrong because the actual hydrogen-nitrogen-hydrogen bond angle is not 90, it is 107.3 degrees. So how are we going to explain this chemically? Because this is the valence bond theory cannot predict the actual shape of ammonia molecule. Now, a successful bonding scheme has to take into account the geometry of a molecule. The geometry of a molecule. For example, a methane molecule has been shown experimentally to have 4 equivalent CH bonds. Now, if we focus only on valence electron, we can represent the orbital diagram of carbon as below. Now, everybody knows carbon is 1s2, 2s2, 2p2. Who is having a problem not knowing this? Carbon is 1s2, 2s2, 2p2. If you have a problem, you let me know in our discussion group in Telegram, and I'm going to cover that. If you're fine with it, then that's okay. Yeah. Now, 2 electrons in the 2s orbitals, 2 electrons in the 2p orbitals. But if you look at this, if you have 4 hydrogens coming in to bond with carbon to make methane, then this is not going to be correct, is it? There are only 2 spaces at which 2 hydrogens can put their electrons, and this is how would a hydrogen, 2 hydrogens go into here? So the scientists have come up with what's called hybridization of orbitals. Hybridization of orbitals. A carbon atom has 2 unpaired electrons, therefore it can only form 2 CH bonds in its ground state. Now, to account for the 4 carbon-hydrogen bonds in methane, which is a very stable molecule, so it must be it can happen. We might excite an electron from the 2s orbital to the 2p orbital. So we excite this other electron. There are 2 electrons in the 2s. We excite this electron to go into this empty orbital. If this is 2px, this is 2py, that would be 2pz. So your 2pz is now going to be occupied by the excited electron that originally occupies the 2s. So you have this promotion of electrons happening here. Now it is getting closer to what the actual picture of methane is. However, this is still not correct, because what you are going to expect to see when 4 hydrogens make bond with this carbon, you're going to expect to see 1 bond different from the other 3 bonds. These 3 bonds will be equivalent. They will look the same, because you have px, py, pz. They actually shape is the same, only orientation is different. But if 1 hydrogen parks 1 electron here, another parks another electron, another here, you expect these 3 bonds, these 3 CH bonds to be equivalent, but this is going to be different. That is what we expect. However, our expectation again proves to be wrong, because in methane, experimentally, it has been found that the 4 CH bonds in methane are equivalent with bond angles. All the 4 bond angles are 109.5. Our expectation that only 3 carbon-hydrogen bonds are equivalent and 1 carbon-hydrogen bond is going to be different is not correct. So after the promotion of this electron into here, another step needs to happen, and that step is called hybridization. That means this S and this P, they are going to mix. It's like if, in analogy, for example, this is a coffee, for example, coffee, and this would be milk, for example. By themselves, coffee is black and milk is white. Correct? But if you mix your coffee with your milk, the liquid that you're going to see is not black, nor is it white. It is a mixture of black and white. You have a nice Nescafe Susu color, right? And it's the same. So if in that analogy, if we mix s orbital and with p orbitals, we mix them up and we separate them into 4 different orbitals, we are going to have 4 equivalent orbitals, which is called Sp3 Hybrid Orbital. This is round, this is dumbbell. So what is the shape of Sp3 Hybrid Orbital? It's neither round nor is it dumbbell. Let's have a look at, after hybrid, to complete the explanation of why you have 109 degrees, we go into the concept of hybridization, introduce that we mix the S and the P and we come up with 4 different orbitals that look the same with each other. That allows the carbon atom to have 4 equivalent hybrid orbitals to bond with 4 hydrogen atoms to form 4 equivalent carbon-hydrogen orbitals, as is observed in real methane molecule. So shape. What is the shape? Now we go into hybridization. I think I'm going to stop here for now. My next lecture, this is going to be lecture 3. My next lecture, which is lecture 4, we're going to go into the shape of Sp3, Sp2, Sp, and so on and so forth. So for now, I hope you understand all of this lecture. First of all, I introduced to you the shapes of atomic orbitals, and then I introduced to you the energy levels of these atomic orbitals, how the electrons are filling in those energy levels following the Outbound Principle, and how from the Outbound Principle the periodic table is the elements being arranged in periodic table in the usual or in the common way that we are seeing at the moment, and how valence bond theory failed to explain the actual shape of ammonia, and why we need to have hybridization factored into our explanation. So for now, I'm going to stop there, and I'm going to then continue in my lecture 4 with this hybridization. Till then, I hope you're keeping safe, you're keeping healthy, and keeping well. Take care. Assalamualaikum.